Hello dear students. So this is another lecture on this complex analysis, complex integration, and today's topic is, if you remember that in previous topic we have discussed about those if we have some definite integrals, we have some integral from some a to b, some f of z dz. So how to solve those integrals in this complex plane? So we have done that. But today's topic is about that if we have integrals which are going to infinite, like we have some integrals from minus infinity to plus infinity, f of x dx. So such type of integrals are called improper integrals, and we will integrate this because we can rewrite this as this integral. We can solve it over the half semicircle above the real axis, right? Because if you so this integral can be written as minus into plus infinity. So in our this classwork we have discussed on how we can write that as r tends to infinity, this closed integral over the surface, because we have two integrals here. So first integral goes from this along this curve, and second goes along the real axis. So that means, but remember that, so first one is that goes over this surface f of z dz. So that will be zero when our r tends to infinity. जब r infinite बन जाएगा, so that means it will lie on the real axis. So this integral will be zero, right? And we have, according to this Cauchy residue theorem, so we can have finite number of poles which are lying above this real axis or below the real axis, right? But we are interested in calculating the residue for those poles which are lying above the real axis, because we are integrating this curve along above the real axis, right? So we have discussed this whole why we are calculating this integral over this above the real axis. So we have done that. We are done there, huh? But our main focus is that, according to this Cauchy residue theorem, we are saying that if you take the integration over a closed curve, so that's basically equal to 2 pi I times sum of the residues, or you need to calculate the residues in that closed loop. So that's basically 2 pi I times summation over residue of f of z. तो यहाँ पे जितने भी residues होंगे, because there can be finite number of poles which are lying above this real axis, so we need to calculate residue at these poles, and that you need to multiply to this term. That basically gives us the value of the integral, because otherwise, if you remember that this is actually minus r to r, because this integral from minus r to plus r, right? Because we have this curve counterclockwise and this goes this way. So that means this is counterclockwise, and this integral is basically this one, that is basically minus r to r, right? But जब हम क्या कर रहे हैं, जब हम r को infinite ले रहे हैं, so that means as r tends to infinity, जो इसका second integral है, so that is basically this integral over this curve s, so it tends to be zero, because when you're stretching it above towards infinity, plus infinity and minus infinity, so it will lie on this real axis, this semicircle, right? So this is what I have done. This closed integral over this the integral over this curve, that's f of the dz, that should be equal to zero. So we have done that in our classwork. So there is no need to prove, because my main aim is to focus on the problems related to those topics. So I'm basically giving you a little bit idea why we are calculating. So how to calculate the integrals, improper integrals over this semicircle, right? So by putting that condition that this r should tend to infinity, right? Otherwise, we should have one more integral which is coming from this curve s, right? So that's why we have only one integral, and then we use that Cauchy residue term. So that means the integral over this real axis, so that can be equal to, that is 2 pi I times residue of f of z. So that's, this is purely coming from Cauchy residue term, and provided that r should tend to infinity, right? So this is what we have done in our classwork. So our today's topic is, that is about, if we take some problems, like if you want to evaluate this type of integral, अगर हमें integral solve करना होगा, right? And the limits are going from minus infinity to plus infinity. So that means we are saying that that r should go to infinity. And one more condition, अगर आपको याद होगा, तो in our classwork, I told you that if you take that f of x, so our f of x is, that is 1 divided by x square plus b square divided into x square plus c square whole square, right? So this f of z, this is rational function. This is a rational, and I add one more point. We assume that the denominator have 2 units more. The order of the denominator have 2 units more than the numerator, right? So this is important assumption that we take here. Otherwise, we cannot integral such type of integral because they can go to infinite. So they don't have a finite value because the limit will not exist at that point, right? Okay, so first of all, so we have this type of integral and we need to solve it over the semicircle, right? So that means we have this kind of semicircle, yeah, over this complex plane. So this is minus after all. Okay, and now first of all पहले हमें देखना कि क्योंकि हम क्या करते हैं, so if you remember that, तो जो इस वैल्यू इस इंटीग्रल का वैल्यू है that is 2 pi times sum of residues. So that means हमें यहाँ पे रेजिड्यूज इसके निकालनी है. तो कहाँ पे, because we can have finite number of singularities or the poles of the real axis, because we are only covering the upper half of this real axis, right? So that means, so first of all we need to calculate the poles for this function, right? So I can rewrite this as, so this integral can be written as, that is from minus infinity to plus infinity. Right? So that means I am taking this. This was above the along the real axis because x square plus b square. I am taking that. It is f of z because it is simply a complex number. We can have this real, but here when we talk about the real axis, we can have only this x part only. That's the real part, right? But I am writing down in terms of that is the complex function f of z dz, right? Okay, so if we compare this with this, so we can have this f of z will be equal to, so that will be equal to 1 divided by, right? So this is our that f of z. तो उसके बाद हमें क्या करना है, now we need to calculate the these residues at the finite number of poles which lie above the real axis. तो हमें वो poles निकालने हैं. तो उसके लिए हमें क्या करना है, जो इसका denominator है that should be equal to 0 in order to calculate the poles, right, for this f of z function. So we'll write the poles for this. So that is equal to, that is, okay, so that means we can have that, so we can have four poles here because at poles our function is not analytic, or you can say that a singularity exists at that point. So we can have four these poles. So we need to check because first of all we need to check which pole will lie above this real axis. So we can have this z equal to plus iota b plus iota c. So it may be somewhere here. So it can be some iota b or iota c, depends upon the value of c. So it's purely a constant, but so you can have these poles which lie within or on this semicircle, right? But if you have a look on these, that's minus iota b and minus iota c. So minus iota b and minus iota c will be somewhere here, suppose. So that means there is no need to calculate the residue as these poles because they are lying outside our domain, outside our closed curve, right? So we need to calculate the residue at these two poles. So that means that z equal to iota b and z equal to iota c, right? So calculate these poles and then substitute it here. Then you write it here, and this basically solves our integral, right? So first of all, let us calculate now residue at. We can calculate that. So we can write that here iota b and iota c lies within contour, right? So that means we can calculate residue at these 2 points, right? So no need to calculate at minus iota b and minus iota c, because it is clear they are lying outside our domain, outside our that closed domain. So no need to calculate at the residue at these 2 points, right? So first I will write now residue of this f of z iota. तो उसके बाद हमें क्या देखना है कि अगर हमें रेजिड्यू कैलकुलेट करना होगा, उससे पहले हमें देखना है कि वी नीड टू चेक वेदर दिस इट इज रेजिड्यू एट ए सिंपल पोल और इट कैन हैव पोल ऑफ हायर ऑर्डर्स, राइट? सो फर्स्ट अगर हम देखेंगे z इक्वल टू आयोटा b, so that means this one. So when we put that z equal to iota b, so it is residue at a simple pole, right? So we can directly write that, instead of this I can write that limit. Right, so this was first part, right? Now f of z is basically so f of z is basically this 1 divided by x square plus b square into this term, right? तो ये हमें सबस्टिट्यूट करना है यहाँ पे, तो यहाँ पे हमें इंस्टेड ऑफ f z हमें ये सबस्टिट्यूट करना है, so that means I can write that residue of okay, so that means we can write this as, so that is r square plus c square whole square, right? So this is very clear, or this will be equal to, or you can write this way. So this is simply the residue at z equal to iota b, right? And इसी तरीके से हमें क्या कैलकुलेट करना है? We need to calculate the residue at z equal to iota c, right? But so you just check if we have, if you want, if you check the function that f of z, so f of z is basically this one. It is x square plus c square ka whole square. So that means we don't have simple pole. It is simple. It is a pole of order 2 here, right? So that means we need to use that in order to compute the residue at residue of this f of z at of the pole have order 2. So you need to write the general formula for that, right? So I can rewrite here. So before that, okay. So you write here the residue of this f of z at z equal to iota c. So that will be equal to, it will be 1 by, that's equal to m minus 1, because we have the pole of order m. So here m is equal to 2 because it has it has a pole of order 2 here. So that means this will be equal to 2 minus 1 limit z tends to iota c d by dz. Right? Because it is that z minus a ka whole square, z minus a raised power m, so m is equal to into f of z, right? And this is 1 by, because we have here it is basically 2 minus 1 and 2 minus 1, so that is d by dz, right? So that means I can write this as residue of right? So this is very clear because जो हमारा एफ ऑफ जेड है दैट इज वन डिवाइड बाई जेड स्क्वायर प्लस बी स्क्वायर इंटू जेड स्क्वायर प्लस सी स्क्वायर, तो उसको मैं लिख सकता हूँ जेड प्लस आयोटा सी इंटू जेड माइनस आयोटा सी, तो स्क्वायर यू राइट इंडिविजुअली फॉर ईच टर्म, राइट? तो इनके लिए अगर मैं स्क्वायर लिखूंगा सो यू कैन राइट दिस एज, सो दिस विल बी इक्वल टू लिमिट दैट इज डी बाई डी जेड right, because this Zalman Snyder's will cancel with this thing, right? So we can have only this two. Now, first you need to differentiate it, so it will take time. So I will write the direct result because it is very easy. So instead of that, you can write that limit that z times to iota c. तो इसको मैं लिख सकता हूँ z स्क्वायर प्लस b स्क्वायर रेज पावर माइनस वन अपॉन z स्क्वायर प्लस, right? Now you differentiate this. So after differentiating and then put limit z times to iota c, right? So I can write directly the result. So what I am getting here, rest of that. So what I get here, so that is 3c square minus b square into iota whole divided by 4c cube, right? So this is what I am getting here, that is 3c square minus b square into iota divided by 4c cube into b square minus c square ka whole square, right? So after differentiating this and then put limit z times iota c, so we will get this. So that means we have two poles here, which lie within that this closed contour, right? And we have two more poles, but at z equal to minus iota b and z equal to minus iota c, and they are lying outside that this closed contour. So we don't. There is no need to compute residue at these two points, right? So only you need to compute the residue at these 2 points. This is what we have done, right? Okay, so that means we can have this integral that minus infinity plus infinity, this integral that will be equal to 2 pi I times sum of these residues, means the residue at z equal to iota b and z equal to iota c. तो इनमें हमें compute करना है तो उनका addition मिलेगा, right? Because that's why I'm putting here summation. So just check here. Okay, so what I wrote here, okay. So because तो यहाँ पे आप देखिए जो हमारा इंटीग्रल होगा, so here that is 2 pi I into sum. So that means हमें जो रेजिड्यू कंप्यूट किया है at z equal to iota b and z equal to iota c, we need to add them, right? And multiply by 2 pi iota. So okay, so I can rewrite this as, so that means we have this residue at z equal to iota b plus residue at z. Okay. So this is equal to, you can write this as 1 divided by plus divided by, that is b square minus c square, right? So this is what I am getting here, because जो second residue आया था that was, oh, okay, so second residue was this one, right? That was 3c square minus b square into iota divided by this thing, okay? And now we need to write that, that is residue of this f of z at z equal to iota b plus residue of So that's equal to iota b into plus 4c cube. Okay. So we can there's little bit of algebra involved here. So you can rewrite this as that is iota divided by, so you take that iota divided by 4 into b square minus c square whole square out. So inside will be that's equal to minus 2 by b plus 1 c, right? Okay, because यहाँ पे मैंने क्या किया, I basically take that iota divided by 4 c square minus b square का whole square out. So from these two terms, तो यहाँ पे बन जाएगा, that is because I have taken 4 out, so 2 will be in the numerator and that's iota, because iota, we have iota here in the denominator. When you put in the numerator, so you can have minus iota, right? So that minus 2 minus will be here and iota will be in the outside this integral, outside this bracket, right? So this is what we get here. So it's very clear. So this is very simple. We can do it, right? So there is nothing great. Or you can rewrite this as, so this will be equal to iota divided by 4 into whole square, that's minus 2c cube plus b into c square minus b square. Okay, so this is what we get here. Or you can rewrite this as, तो अब मैं क्या करूँगा, I can multiply this to this term and we iota you take it out, right? So that means I can rewrite this as, so that will be equal to c square into c minus b. Okay, so that means I am basically rearranging this. So I am just doing little bit that arrangement here. So I am multiplying this denominator by this term and then you assemble it. So then you can divide this way because c cube minus b cube. That means, so c cube यहाँ से आ रहा है because c cube 1 is coming from here, right? And b cube is coming from here because we have this b cube, this is minus b cube, right? So it is coming from there, that is c cube minus b cube minus 3. So you just check whether this is correct or not, right? So this is very good. So this is very straightforward. Okay, or you can rewrite this as, that will be iota into, you can take that c minus b out, right? So inside will be, that will be c square plus b square plus bc minus 3c upon that. So I can write this way. Or so if you do a little bit more modification, so this will be minus iota into b plus 2c divided by, that is 4bc cube into b square minus c square का, right? So this is what I am getting from here, right? And okay, so this is what I am getting here, right? So that is minus iota into b plus 2c divided by this term, right? Okay, so now you need to put, because if you check that, so in our that problem, so it says that we need to put it for this. Okay, so we need to put for b equal to 1 and c equal to, right? So that means you can write this as for b equal to 1 and c equal to 2. So when you put b equal to 1 and c equal to 2, so b equal to 1 is, it is 1 plus 4 because c is 2, so that's 1 plus 4, right? So okay, let me write it here because I cannot continue with some more. So better is to write here, huh? So that means for b equal to 1 and c equal to 2. So this will be equal to minus iota into 5 divided by, that is, when you multiply it by, so we can have this 2 into 8 into 9. Right, so it will be 5 iota divided by 144. Right, so this will be our, okay, so yes, 5 iota, huh? 5 iota into divided by 144, right? So that means, so this one, that integral, that minus infinity to plus infinity, that is dz upon z square plus a square plus b square, sorry, into z square plus, that is equal to this. So ये हमारा ये इंटीग्रल था. I will calculate that for b equal to 1 and c equal to, or you can further modify it if you, अगर आपको prove करना होगा, so that means if you, because this is an even function, because if you put that z equal to minus z, so you will get, because it's even function, you can write the integral from 0 to infinity, and then that is twice, right? So that means integral from 0 to infinity. So this is basically for when you put that z equal to 1, right? So z equal to 1 is, okay, so there is this term, so we need to modify it. So we need to write it because this is z plus 1 plus that 4. Okay, so this is also integral, right? That is z square plus 1 or z square plus 4, right? So this is how you can solve such type of integrals while your limits goes from minus infinity to plus infinity, and you can integrate it over that semicircle which lies above the real axis, provided the condition is that our r should tend to infinity. Then our that then this integral over this okay, so when you put that condition that r tends to infinity, then the integral over this curve s, so it will go to 0. Then we can write directly from Cauchy residue theorem that integral over a closed curve, that is equal to 2 pi r times into sum of residues, right? So but remember one more thing, that basically I add one more point, that f of x, it is rational, and so it is a rational function, and your denominator should be 2 units more than the numerator. So this is very clear because तो जो हमने function consider की है, our f of z is some p by q form here, right? And our denominator, it has this power order, it is 2 units more than the numerator, because in the numerator we have some x raised power 0, right? So this is the first assumption, because otherwise the limits will not exist in that case, right? So this is how we can solve these type of integrals where our limits goes from minus infinity to plus infinity, like improper integrals. And in addition to that, in our coming lectures, we will focus on some problems, some improper integral also, but we have some sine and this cosine terms multiply. So that means we have some this trigonometric functions multiplication to our that our function that is basically rational, right? And but that is also that improper integrals, because वहाँ पे भी limit हमारा होगा from minus into plus infinity. But in addition to that, we have this f of z, but in addition to that, we have multiplication that cos z and sin z. So in order to solve such type of integrals, hopefully we'll, in our coming lectures, we will focus on such type of integrals, and we'll really focus on the problems, right? Thank you very much.